Smart contract security, great. Patrick Grave, that's me. Who am I? Quick intro, because Leo's intro, I'm not a world-renowned anything. I'm a second-year science student, Melbourne Uni, studying maths, probably in stats. Good set of subjects, but you know, it gets a little dry at times, but side, which is quite good. I like reading about cybersecurity. I'm a member of MISC, which is the better MonSec at Melbourne. Love messing around with computers. Leo can attest to that. I frequently mess around this server and just and play with the files there, and I don't think he appreciates it very much. And technically, I am a part of the CTF team Skateboarding Dog, which is a whole bunch of MISC members. But I definitely don't put my word on that team. But it's good. It's good fun. And on GitHub, I'm Hydraulic Sheep, and on Discord, a random guy if you see me around. I am in the MonSec Discord, in the private. I don't know which chats I'm in. I'm in the ones that are for visiting members, so you can say hi to me there. So yeah, let's start with what are smart contracts. Just quick intro for people who I suppose haven't learned so much about this before, because this isn't really my area of expertise. I just did some reading. And so smart contracts, right? They're pretty simple. They're just programs that run on the blockchain. They have kind of state, so variables which are public or private, like any program, and they have kind of money associated with them on the blockchain. So we'll be talking about specifically Ethereum here, because it's the most popular platform where smart contracts run. So Bitcoin does have kind of some smart contract features, but they're not as versatile. I don't think the language is Turing complete, and they're not as versatile as Ethereum's tools. And Ethereum kind of pioneered the system as well, and so it's a more popular platform for these kinds of utilities. And many newer blockchains have introduced this sort of technology because it's quite useful. Attaching kind of functionality to the blockchain through these programs, function handy, good utility. And there are good tools for working with Ethereum, which we'll get to later. How do they work? So on Ethereum, we have a whole bunch of these languages, right? And it kind of bears some resemblance to your traditional programming languages. So we have Solidity. This was the original kind of start off, what people started working on. It's very popular. And we have some kind of other alternatives which are newer, and they have their own perks. So Viper, it has some safety checks, simplicity, has strong typing. So does, I think, actually, I don't know Solidity's typing situation, but Yule, which is more assembly-like, lower level, and you can use it for inline assembly in Solidity. And then Fave, which is this Rust-style language that's extremely new. And Sai is in the chat, you can get a shout out for that one. And we'll be looking at Solidity because it's got good tooling. It's quite popular. The dev communities are really nice. And it's easy to make errors. And that's kind of why I'm here, because smart contract security is all about, and I'll get to a bit later, is about the errors you can make in normal programming, really, and some unique things to the blockchain. So there's some delegate calls, which we'll look at later, which are witchcraft that I haven't got my head around yet. And also things like randomness on the blockchain, where there is no kind of, the sources of randomness aren't necessarily very good. And so we'll be looking at that a bit later. Awesome. So here we go. We've got some quick Solidity code, which is I'm going to use as a crash course for everyone here. This is going to be like a more interactive workshop when we get later on. So I hope like everyone can be able to go onto the site, do some challenges by themselves if you've got a little bit of programming background. And so I'll just kind of run through this. So this is a sample kind of smart contract, right? This is the typical vending machine example straight from Ethereum's website. And so we have here our contract, right? Well, firstly, we specify our, can you guys see my mouse? Yes? Could someone say in the chat if they can see my mouse? Oh, okay, I'll see the chat. Yes, awesome, okay, great. So up the top here, Pragma Solidity, that's just specifying the compiler version you want to use. Pretty simple. You can actually specify a range of versions that it will work on up to next major release. And so, yeah, pretty handy. We have our contract, right? The syntax, if you recognize it, you might think it looks, or the object-oriented nature of it is quite similar to something like Java or any like traditional object-oriented language. We have our constructor for the class. So if you think of a contract as kind of a class, we have a constructor down here for our class. A public constructor, you can have constructors which aren't public for an abstract class, but we won't be dealing with those here because I think we're just going to start things simple. And then we have these kind of public variables. So we have this mapping between addresses. So those would be accounts on the blockchain. And so those might be a wallet or another contract or something, into some sort of integer. And so here we have Cupcake balances as our value that's stored. And then once again, we have an owner address, which is whoever's kind of created the contract. And so once again, this owner is initialized by this message.sender, and message.sender there is kind of this special variable. And so when the constructor is called, the message and the transaction are both, so MSG and TX are both information that's passed to the constructor, and it's passed on every kind of function call. And so the message.sender is whoever created the contract, the person who actually called the constructor. And there will be some differences later on between message.sender and transaction.origin, which we'll look at. And then here we have the Cupcake balances are just assigned to 100. So yes, it probably looks familiar to people who've used programming languages before. We have a public function down here and another public function. This one is marked as payable. And so as of newer versions of Solidity, if you're going to no, sorry. So here we have our public function. This require will cause the transaction to fail if you don't meet the requirements. So if you're not the owner of the contract, and then we do some assignment. And similar behavior down here. Another requirement here, our message.value. So the value we attach to our transaction must be greater than or equal to the amount, the number of cupcakes you're buying times 1 ether. So you must be paying 1 ether per cupcake, or at least 1 ether per cupcake. I suppose they'll try and stinge you out of more money if they can. And then, yeah, we check the cupcake balances. So it's fairly simple. And from, if you've kind of worked with Java before or other object-oriented paradigms, it probably feels quite comfortable. Awesome. Tech specs, if you actually want to read into the details, this is the place to go. This is the definitive standard, the Ethereum yellow paper. The white paper was kind of released in 2014, I think. I might be wrong on that year. It was more a broad overview of the kind of concept of Ethereum. And this yellow paper released by Gavin Wood, I think 2014 also, kind of really outlines the specs. It's not the nicest document. Well, I know it's a very nice document, very solid. It's 40 pages or so, but it's I find it difficult to get through. So yeah, if you're into that sort of thing, be my guest, have a read, and I'm sure you'll get a lot out of it. Cool. So the challenges we're going to be doing today, I told Leo we'd be doing Capture the Ether. Because I did those challenges a few years back, and I thought they were quite good. But I had some difficulties yesterday dealing with the Capture the Ether kind of platform. I think the test network that it's based on, just for context, sorry, Ethereum, when we talk about Ethereum, we're talking usually about the main kind of network. So where you kind of trade Ethereum for USD or whatever, right? That kind of main network where Ethereum transactions really happen. That's what we're talking about. But for development purposes, there are a lot of kind of development networks, they're called. And some of them are specific to a certain client. And so they'll be run by kind of the client's maintainers. And then there are some, and they often, there are a few of them that rely on proof of authority rather than proof of work, which is just a different verification standard and makes it less secure. And so the test network that Capture the Ether forced you to use, where all the challenges were based, was quite slow today, and I had issues yesterday and today. And so I just, Ethernaut, the challenges actually I find a lot better, and so I think they're quite good, and they actually are quite usable, which I find quite nice. So Ethernaut. So Ethernaut is a Web3/Solidity-based war game based on Over the Wire. So if you played like NATAS Over the Wire, great set of challenges. Do that as well if you want. But yeah, similar kind of concept. And then you play in the Ethereum virtual machine. So each level is kind of a smart contract that you need to hack or pwn. And yeah, open source, and you can contribute levels. And some of the later levels are really kind of, I can't do them myself. I'm trying to, I think I got up to level maybe, no, I don't think, I think I got maybe 16, 15. And then like, that's all I had time for. And so I kind of stopped there, but they are very good challenges, and I would recommend taking some of them in your own time and having a go. Cool. And so we'll get onto the challenges in a sec, and I'll do a few walkthroughs and take questions. But common smart contract issues. Just kind of some context on what we're going to be focusing on, what to look out for. Generating random numbers, big thing. Because on the blockchain, right, all your information all the places you're getting information from are usually public sources. And so you might consider, say, getting timestamps from different blocks and hashing those, or getting the block hash of the previous block or something like that. But that doesn't like, it's very easy to kind of replicate that random number source on my end and reproduce those random numbers at the same time, and therefore kind of it ruined the point of the randomness, because I can just steal your RNG. And so we're going to look at how that's done poorly and how that's done well. And then also we have kind of your standard programming bugs. Buffer overflows, not so big. I probably should put integer overflows down there because, yeah, they seem to, Solidity is not a language which is, Solidity is a language like C in a way, or I don't know actually. I don't know what Java's deal is with integer overflows. You'll have to tell me, but yeah, integer overflows in Solidity are a concern, and so something to keep in mind. And then misunderstanding the spec, and so standard kind of programming errors, not understanding what's going on. And then finally, we have maths and calculation errors, and so that's probably tied to integer overflows as well. And so we're going to look at some of those. And so, yeah, overall, it's fairly similar to crypto or Pwn challenges in CTFs, where you need to kind of spot a vulnerability in the code, but it's based on your understanding of what's going on. And so that might be, how Ethereum works, and you know what this function does and why they're using it wrong, or you might need to do some reading on a certain method and see why their use is incorrect, and kind of do that slow process of debugging and figuring out where their issue is. Cool, and the tools we'll be using, which I'll kind of guide you guys through, MetaMask, which is an Ethereum kind of wallet utility, which you can have in your browser. Etherscan, we won't be using that one so much. That's more useful if you say using it for something other than these CTF challenges. And then the Remix IDE, which is really handy. That basically is an IDE for Solidity in your browser. You can, of course, I'm sure, write it on your own. I can install a compiler for Solidity on the machine. I haven't, because I don't know, I just found the Web IDE really handy, and I didn't really want to deal with compiler configs late at night, and so I'm using the web-based one. Awesome. So we'll get started. So first challenge, I have switched to my other kind of. So this is MetaMask here, which I'll show you in a sec. I have switched to my other account on the test chain because I didn't want to, I want to reset the challenges, and it is affiliated with your kind of account. So yeah, first thing you need, and feel free guys to do these challenges alongside me, or kind of skip ahead or do whatever you like and ask questions in the chat, because I know it's hard online to do kind of an interactive style workshop. I'd love to be in person in the Monsec. I've never been to the Monsec rooms, but I'd love to come and do a workshop in person. But yeah, if you'd like to work along in sync with me and kind of follow these steps, it might be a bit less tedious, I suppose, because you get to actually interact, and that's more fun. So yeah, first things first, MetaMask, browser extension, pretty simple. You just go through the installation instructions, click download here, and it'll take you to the page for your browser. I'm using Firefox, better than Chrome. Okay, it isn't, but I wish it were. And yeah, if you want to install MetaMask, you just go to the extensions page and get it installed. And it will ask you to make an account, and then you can go through those steps. It's fairly simple. And then the next thing you'll need to do, actually, which they kind of keep, they put down here, but I will kind of do it now because it's an important step. For people who aren't familiar with kind of blockchain or Ethereum or Bitcoin or anything, on the Ethereum blockchain, to kind of make all transactions or call a function in these smart contracts, you need to pay a little bit of a processing fee or transaction fee, right? And that's in the form of gas, right? And so gas is just a term for it. And this kind of fee, you can actually vary it a little bit depending on how much you want, how quickly you require the transaction to be processed. So it's an incentive for people to process your transactions, really. So if you want speedy delivery, you can pay a little bit more and get a quickly executed transaction. But the long and short of it is to kind of do these challenges, you'll need a little bit of test money, right? And that's just given out on the by what's called a faucet. And so if you go to a site like this, we're using the Rinkeby, I don't know how to pronounce it, Rinkeby test chain for our kind of tasks here, because that's the site that Ethernaut uses. But yeah, if you want to take part in the challenges to do them, you'll need some Rinkeby test ether. And so look for a Rinkeby faucet or the link I sent in the chat, which is one. Awesome. And so first things first, this MetaMask provides a very nice set of tools for these challenges. And so we can go to our console here, and the UI looks a little strange. It's got a style to it, I can tell you that. And so this actually gives us a lot of kind of helpful utilities, right? And so this is my kind of wallet address for my MetaMask account. And so there's a whole bunch of other helpers. So we can call the help function here. And it has this list of helper functions. And then we can actually, one of these helper functions here is get balance. Very handy function. It means I don't need to kind of go off to something like Etherscan, which I'll show you in a sec, and look up what my balance is, or say another account's balance is. So player stores my wallet address. So let's have a look at get balance player. And you'll notice that because we're using JavaScript and these are all asynchronous, it returns it in the form of a promise. So you probably want to call await before all of these.
So I don't think we can see what you're typing.
Oh, you can't see the dev window, can you? Ah, okay, sorry. I will reshare my screen. Thank you. Thanks for pointing that out. I'll just share my whole desktop. Awesome. Can you guys see my screen?
Yep.
Okay, cool. So here we go. So this is kind of the funky UI. And this code injected, some of this is injected by Ethernaut, but MetaMask injects some of these utilities as well, allowing you to use JavaScript in your browser to execute functions. Anyway, so I'll just run through that again. So here, player stores my kind of my address for my wallet, and then these help functions will be helpful in solving these challenges. And so you can see that there's this is the main contract for the game. There's a level contract. This is the contract instance. That's all right. And then we have these helper functions, which are to get our balance, to get the block number of the current network. So that's the latest, the number of the block that's been latest mined. And so we can check what that is. Here we go. Oh, okay, yes. Like I was saying, you want to call the wait before all of these. There we go. Okay, and if we wait a short while, then we might have another block mine. I'll get back to that. And then we can send a transaction via this and put in some options. We'll use that later. We can get the network ID. That's not so important. And then we can do these conversions here, which are quite handy. So Wei is the smallest quantity of Ethereum that you can transact. I don't know. I think I don't know how much Ethereum is in terms of powers of 10. It might be 10 to the minus 16. I'm not sure. But it's quite a small number. Anyway, so let's have a look. So look, we've mined 3 more blocks on the test chain since we last called that function. Awesome. Okay, and so it goes through some of these utilities here. So we have our console helpers that I just showed. Oh, something in the chat. 10 to the power of negative 16. Sorry, Luke St. John, thank you. Yes, 10 to the power of 16 is not a small number. Good catch. Yeah, the Ethereum contract. So the Ethernaut contract, we don't need to mess around with this very much. That just kind of is how this all is running. It's running on the blockchain. And then, so this, what we're interacting with here, when we kind of look at the Ethernaut contract, is one of the core kind of Ethereum concepts that we'll be dealing with later on. And so that's what's called an ABI, which stands for, what does it stand for? Oh, 1 sec. I should know this. Let's have a look. I should know this. Hello, here we go, Solidity. Anyway, our 2 components, there we go, application binary interface, right? The 2 components of our kind of Ethereum contracts are this application binary interface, which tells us what the functions are in our contract, what the kind of data types each function expects are, and it tells us how to interact with the bytecode that is put directly on the blockchain. So all that's on the blockchain is not this source code that you write, just the compiled bytecode to the Ethereum VM. And then you have to interact with it. You need the help. You need the help of this API to interact with it. Awesome. Okay. And so by this point, you might have got some test ether. You might not have. All good. You just need some to take part. And so finally, we get on to this levels challenge, which is kind of a hello world. So first thing we need to do is we need an instance of the challenge. So what this does is this uploads, this creates an instance of the contract on the blockchain. So it creates a new contract for us to work with for the level. So this is like creating the level for us. And so here we see this MetaMask pop-up. I'm going to be transferring 0 Ethereum. It's going to have a very small suggested gas fee. I'm just going to pay the suggested because the processing of this network is very fast. And it should be fine. So here in our little window, we've got this helpful kind of challenge assistant. Hopefully this shouldn't take too long, so I'd like to get on to actual challenges. Any questions so far while we're waiting for this? All good. Here we go. So we have our instance now. And so this will be our contract object. Let's have a look. So here we have the details of the contract. We have this ABI here, which is what we were talking about before. And if we scroll down, the source code of the contract is actually hidden, but in all the other levels, you should be able to view it. And that's just, I think, to get you familiar with using this web console to start off. So if we have a look, we can actually call the methods of the contract via this JavaScript console, and we'll later call them using our IDE. But let's have a look at interacting with them for now. So let's call this. So right, it tells us to call info1. Here we go. Let's call info1. And now it tells us to call info2 with hello as a parameter. Okay. So we can pass in parameters as an argument, of course. Okay, the property info num holds the number of the next info method to call. Great. And so we've got our object back. Here we go. And the number is 42. Okay. So now we probably want to call info42. I'll pass in hello again. Okay. Yeah, it doesn't want hello. Great. Cool. The method name is the name of the next method. Awesome. And this isn't really a challenge, but it's just getting us familiar with this interface. Okay. And then now we need to know the password. Okay. Now, if we look back at what this, what we had access to in the ABI and what we have access to here, password is a function we can call. It's a public function here. We can have a look at this. When we get the source code, this is a lot nicer, but this is a public function we can call. So let's call await contract password. And that's our password. And now we'll lastly call, and I don't need to call await. And lastly, we'll call authenticate and pass in our password. Now, if you've been paying attention so far, you've probably noticed that for all of these, I didn't have to, this MetaMask thing didn't come up. I didn't have to pay any Ethereum. And the reason for that is, which we'll get to later on, is those are all, what we were doing there is we were calling those functions rather than making a transaction. And the difference is a call is a kind of local simulated non-read interaction with the function. And so you can indicate that in Solidity. That should have worked. So now we've authenticated. Let's just submit this challenge. And once again, we have to pay this. This is all right. But yeah, so yes, when we call those functions, we're kind of interacting with a read-only version. We're not making any changes to the chain. And so it's suggested, like if you're interacting with these functions, it's always best to kind of make a call to them because you don't exactly know if you need to make a transaction. And if they're marked as pure or constant, then you don't need to. So yeah, here, this is the source code of what we were just interacting. So we had these functions marked as pure and public. So they were public, so we could interact with them. And they were pure, which meant that they didn't actually interact with the state of the contract. And so that's why we could interact with them without transacting there. Cool. So fallback. So this is the first, I suppose, real challenge. Let's get our instance and let's take a look. So we have our source code down here. So here we have our source code. It looks perhaps a bit daunting. Let's have a look at the challenge. You need to claim ownership of the contract and reduce its balance to 0. So we might have a look through this and try and identify what's going on. We have our constructor. The owner is assigned as the message sender, fairly typical. And then we have this contributions variable set to 1,000 ether, right? Just a variable. We have this modifier, right, which checks if the sender of the message is the owner, and this will be required later on. We have this function contribute, which can be called by anyone because it's public, and it requires that the value of our message is less than 0.001 ether. Okay, and then we have these kind of things down here, checking if the contributions to the message sender are greater than the contributions of the owner. And we saw what these were defined as before. Contributions of the owner, right, message sender, were set to 1,000 ether, right? So to get this bit of code to execute, we're going to have to contribute 1,000 ether, which doesn't sound very reasonable to me. I don't have 1,000 ether floating around, or even 1,000 fake ether like we have in these challenges. And so we probably want to look somewhere else. Get contributions will tell me how much I have contributed. We can withdraw money, and this receive function here, right? And so this is a first kind of look into ways to mess up into Ethereum. So receive is what we call, it's a fallback function, right? And so it's a type of fallback function. You might have heard of fallback before. A fallback function here is when your request doesn't match with any of the other functions. And specifically, receive only falls back when you attach no data. So basically receive is a function in Ethereum, or in Solidity, sorry, that lets contracts behave as just wallets, right? You can transfer money to a wallet and you can transfer money to a contract without kind of interacting with any of the functions. It's just a chill way that lots of contracts can just accept money. However, here they've kind of implemented some weird logic in the receive function. So we have requiring that our message value is greater than 0. Okay, that makes kind of sense. And the contributions of the sender is greater than 0. Okay, and then it assigns the owner to be the message sender. Now that seems like a bad idea for something that is publicly accessible, and you can call if you have you send any money to the wallet. And so let's have a look at how we can interact with this. So we'll start by using this JavaScript terminal, just because we'll move on to Remix a little later. And so first things first, to actually meet this requirement statement, we're going to have to check that our contributions are greater than 0. And so the way we do that is we contribute here, because this will set our contributions to be the value that we send. So it's actually fairly simple to interact with this console here. So we're going to contribute. So we need to contract dot contribute. And then we want to pass in the amount that we're going to contribute, okay? And it needs to be less than 0.001 ether. That's what that requirement is, okay? So let's pass in, it's an extra 0, and hopefully that should be fine. Oh, invalid number of parameters for contribute. Why is that wrong? One sec. That shouldn't be wrong. Wait. Hello. I think. Oh, okay. I know. I think contract contribute. I think the reason is I need this data object. And so set our value to be 0.001. Should work. No, it's even worse. Let me just have a look at my notes quickly. I did do this yesterday and it was not that bad. Let me have a look. Okay. Oh wait, can you guys not see my screen anymore? Okay, that's not very annoying. The live demo gods are merciless. Yes, I agree. Thank you, Leo.
Leo can relate to this situation.
Yeah, I'm sure he had good luck. I remember he had good luck 2 weeks ago. It was good fun.
I relate way too much.
Awesome. Okay. Let me share my screen once again. This is annoying. Actually, give me a moment. I'm going to attach my other monitor. Hopefully, this should work. Okay. Sorry about the delay. Has anyone actually been in the chat? Has anyone actually been trying to, has anyone actually registered a MetaMask account? And has anyone been going through the challenges?
Yeah, I've been trying to go through them, but it took me a while to get Faucet to work.
Yeah, that's fair. Did you have to tweet something to your Twitter or something?
No, I found a different Faucet. Didn't want to tweet anything.
Yeah, fair enough. I didn't want to tweet anything either. I used my old Twitter account. Okay, awesome. Okay. Hopefully sharing should still work on my screen. I'll just get this up. Here we go. Let's get back on the whole desktop. Okay. Okay. Now let's get this back up. Awesome. Okay. Okay. Right. So what we're trying to do is we're trying to contribute we were trying to call this contribute function, right? Okay. Well, let's try that again. Our contract should still have an instance because we instantiated it before. Yep. Awesome. And then, so we want to firstly call this contribute function, right? And so what we want to do is we want to and I think it actually takes, no, okay. Why is this not? Okay, we might just take the remix approach then because I did this by the IDE and we can introduce that now. That's all right. That's okay. Cool. So let's actually try this from, oh wait, no value. There we go. Okay, right. So yeah, the reason we had our issue there is because we needed to pass this as the data of the transaction, right? Rather than, if you notice here, the function isn't actually taking any arguments. It's looking at the message value, right? And so message value is one of the data objects you can attach by passing in data. Thank you, Gautam. Yeah, you're right. I need to pass way. I needed to convert it to way. That's correct. Awesome. Okay, that transaction could go through. Okay, and now after we've passed that transaction, we then should be able to actually interact with this receive function down here without getting bounced by the requirement. Awesome. Okay, let's have a look and hope this processes fairly quickly. The Ethereum isn't great for a demo. I'm not going to lie, because you have to kind of pause and wait for things to process, because there will be that short delay. Awesome. Oh, it did go through. Okay. I didn't hear the sound effect for some reason. Okay, cool. And then now we can check that we actually contributed by calling this get contribution function. Let's have a look. So now we can have a look. Okay, we've contributed some money, right? This is trying to represent an unsigned int in terms of an array, but that's all right. We've contributed some money. Okay, and then we can now just call our contract, and then we can send a transaction, right? And we can specify our value as, once again, two-way, and then let's specify a similarly small amount of Ethereum. And once again, hopefully this will process fairly quickly, if I actually pay attention to whether it's processing or not. Awesome. And so what's happening here is we're sending some money to the just to the wallet address, just as a general transaction. We haven't specified a function or anything that we're trying to call. And so now what will happen is, because we haven't specified any data except for a value to the transaction, it will head to this fallback function, and we will pass this check and will be signed as the owner. So we can now check the contract owner. And that is our wallet address that we're using before. So we can have a look. That's our wallet address. Awesome. So now we'll just verify that we've solved this challenge. And we might skip to the next one. Well, sorry, we might skip the next one to coin flip, which is a slightly more interesting challenge. Because it is about randomness, as coin flip would suggest. It should be submitted in a sec. What? Okay. Yes, we have. What? That's us. Okay. Oh, wait, actually, we had to reduce its balance to 0. That's all right. We'll move on. This just involved calling the withdraw function that we can now that we're the owner. Yes. Thank you, Sai. We're going to move on. Awesome. Okay. So let's have a look at this. We'll generate our instance while reading the challenge. Awesome. So coin flip. There's a coin flipping game where you need to build up your winning streak by guessing the outcome of a coin flip. At this level, you need to use your psychic abilities to guess the correct outcome 10 times in a row. Now, I don't know about you, but psychic abilities don't seem fairly likely as a way of solving the challenge. And I don't also think that guessing 10 coin flips in a row is statistically very easy. And so we're going to have a look at the contract. We're importing this safe math library. That's not so important. That's just a library online. We can go and look that up later. But that's just fairly standard. Shouldn't ring any alarm bells. We have this big factor. Okay, we'll see what that's used for. Constructor, which sets consecutive wins to 0. No kind of owner behavior here. And then we have this line. So this function, which is our flip, we're returning a guess. And the instruction is we have to guess 10 times in a row. So let's have a look. UN62256 block value. Okay, that's a fairly big number. I don't think we're worried about overflows here. And we're looking at this expression here. So for context, this sub is a safe math function. So it's just a way of subtracting without to avoid overflows in a safe way. So that's nothing to worry about. But what we're doing here is we're taking the block number that the transaction is in, and then we're taking away 1. So we're looking at the previous block when the transaction is executed, and we're hashing the previous block. Oh, sorry, we're getting the block hash. No, we're getting the block hash. It's already calculated. It's on the chain. We're getting the block hash of the previous block. And if we have a look, if the last hash is the same as the block hash, we'll revert. So we can't kind of use the same hash over and over again because it saves it after 1 execution. So we can only execute really once per block. And then here we have this coin flip. And so we divide the block value by the factor, that big number up there. And this block value we calculate it up here. And then we check where the side, we check where the coin flip equals 1, right? And so here we have our coin flip value, we're checking with our guess down here, right? And so what we're doing really is we're kind of trying to get a source of randomness from the blocks, right? The previous block number, which doesn't seem like a good idea, you probably think, because the block number is publicly accessible information at the time that your transaction is executing. And especially because you can actually call this transaction after knowing the block number. And the way we can do that is by writing our own contract to actually manipulate this. And so I suppose for an explanation of why this is a bad idea is we'll think about how the transactions work. So first, what we could do is we could start off, I don't know why this pen's in black. Okay, right. So we could start off with, say, our contract up here, right? Which takes in, say we make a guess, right? So say we make our own contract, this red box, and we want to, we have this other contract, the blue box, which is this one here. So this is our kind of, this is our blue box, right? And this red box is something that we own. And so if we think about what's going on, right? In this red box, right, which we've kind of submitted to the chain, right? This is our transaction. Sorry, in this red box, which is our contract, we can submit a transaction to this contract. And we can say, let's guess true, okay? Let's guess the coin's gonna be heads up, right? true or false. It's just a Boolean number. And so let's say we guess true. What we can do is we can then actually check the last block value. So our contract can go and look at the chain and say, okay, the last block value was, let's say it's 200, right? It's a very small number. The block values we were looking at before was much larger than that. Okay, the last block value was 200. Okay, now we can do this hashing ourselves, right? Okay, we'll hash out 200, and then we can then we then have this value for ourselves in our red function, right? And the blue box is going to calculate this separately. So we have this, and then we can ignore this, right? That's something we can get around by just executing over and over again, as long as we don't use the same block. Okay, and then here, the coin flip value is the block value divided by the factor. Okay, so we already have this block value. We have this from up here. We can calculate that. And then once again, we can divide this by our factor because we know the factor. It's up here. It's on the contract. And then once again, then we can do this comparison because this is just checking if the coin flip value equals 1, true or false. And so we can do that as well because we've calculated this, and that's all we need for that. And so we've got all these numbers, and then we say we put in our guesses true. We know what the side is, so we know whether our guess is right or not, right? And so if our guess is right, we can just pass it on to this function. Contract is we can, or smart contracts on the Ethereum blockchain is we can call other contracts from our contract. So we can call other functions, other contract functions, right? And so because of that, we can call this flip function in the real contract, right? And actually just use, get the number always correct because we can change our guess if our answer is wrong. And we know whether the answer will be right or wrong. And so we can always pass the right value to the correct contract. So I think we've got a strategy, I suppose. We know that the block value, the last block will be the same for this contract and this contract. And so we can use that because our source of randomness will be the same and we know what the randomness is. And so let's have a look at how we'd exploit this. So I've already written up a solution. I think this is number 3. Yeah, I've already written up a solution, but let's kind of, I suppose, take it from scratch. So let's make a folder. Actually, we don't need a folder. Let's not do that. Let's make a file. And so the first thing we want to do is we actually want to we want to take in this coin flip contract so we can use it as a so we can interact with it in our code. So just copy paste into our IDE. And so here we go. So this is coinflip, coinflip.sol. I don't know why it opens all these folders whenever I create a new file, but that's all right. Okay, here we go. And then one thing we just have to do as a matter of, because this IDE doesn't support those, this kind of notation, I've written down the direct GitHub URL to that library, which is right. And so here we go. Let's just remove that. Awesome. Okay, cool. So that would be our URL to our library. And then we have our coinflip contract here now. And then I've set this on the left here. This is our compiler, right? We've version, so, and I've set it to auto compile. So it should just automatically compile this whenever we kind of interact with it. And so now what we can do is we can actually put in the address, which we got here, our instance address, in this run tab. So you want to go to the deploy and run tab and then go down to this @address button, coinflip, and click this. And this actually, all this does is it's actually just, we're telling the IDE that we've got a deployed version of this contract at that address. And this refers back to what I was saying before about ABIs and bytecode. So each contract on the blockchain, you have the interface, right? It's called an ABI, which is similar to API because they serve similar things, right? You have our bytecode, which is the actual thing that runs on the blockchain. It's stored on there. And then you have this ABI, which actually tells you how you can hook up with that bytecode, how you can interact with it. And so by putting this code into this IDE, the source code here, we're telling the IDE that these are the functions we're expecting. And then we're telling the IDE, this is where you can find them on the chain. So we kind of need to, we could actually put any address here and they would, the idea would believe us because it's not doing any checks really. But we might fail when we actually try to execute it in the functions down here. So I suppose right now we could take a guess if we want. We could guess heads or tails. Let's guess true and just take a guess. I think this is probably done. Here we go. Okay, it's going to give us our MetaMask. Okay, we're going to guess true. Let's see if we were right. Probably not a good strategy, but we just want to show it's working. And then if we go to the contract, we can actually see consecutive wins is incremented each time we get the guess right. So we can actually just check the consecutive wins variable. So our thing went through. So let's have a look at contract dot consecutive wins. Let's await that. And here we go. Oh, look, our number's 1. So we did get the guess right. Lucky us, right? I don't think that's a good strategy in general. Let's write a script like we're using our tactic from before. Awesome. So coinflip.sol was our kind of coinflip script, and let's call this exploit.sol. Okay, awesome. And it opens all the folders again. Of course it does. Cool. Okay, so we have exploit.sol. I'm going to just copy some of the syntax here because we want a fairly similar we want a fairly similar contract. So let's just name this contract. We'll call this Ethernaut 3 exploit. Okay. And then we have our constructor. We don't need this. We don't need this either. Or this, we just need the inspector. Awesome. And then so the other thing we do need is we need a reference to our contract that we've deployed. So our CoinFlip contract, so we can actually call functions from it later on. And the reference from the contract will look like this. Okay. So the syntax might be unfamiliar to you because you might want to do some Googling, but I've kind of noted it down because I also had to do Googling. So the correct syntax, we want to import our CoinFlip. Okay, so let's import this. So we've imported our CoinFlip, and then now we want to CoinFlip. And so just as you might in Java, right? This CoinFlip is being treated like a class. Right? So you behave it, you treat it in a similar way. So this CoinFlip actual coin equals CoinFlip, and then we pass in the address of where our CoinFlip is stored. So here we go. Awesome. Okay, and now let's go back to our compiler. And then now, okay, so we've got our kind of details we need to successfully do this. Let's write our exploit. So our function, let's call it, I'm going to get off this. Our function, let's call it fake flip or like guess flip. We're going to pass in a guess here. Okay. And so this is where we write our attack. And so all we really want to do is we want to copy the logic over from our CoinFlip because we just want to repeat what they're doing to generate these random numbers, right? And so let's take all of this up here. We don't need this because last hash is not in our code. And so we're left with just these 3 statements, right? Which is where they generate the random number from the block, last block, where they actually divide this to kind of find this different CoinFlip value, and they compare it with the, and then they compare it with the, they compare it with 1 to check if it's true or false. Okay, and then so here we have this. And so what we want to do now is we now just want to change our guess if our guess is wrong, right? So here, we also want to copy over this logic. Fairly straightforward. So we have our guess is not called underscore guess, and we don't have consecutive wins. But what we do want to do is you want to call, this indentation is killing me. I don't know what's up with this. No, we don't need this. Okay, so here, do I have too many curly braces? Maybe. Okay, so here, if our guess is correct, right, that's what this means. We want to call the CoinFlip guess function with our guess, right? Because we know it's correct. So let's look at the coin flip function. It was called flip. So we want to call our actual coin dot flip. Actually, that's not how I think this is kind of guess. And then if our guess was incorrect, that's fine. We just want to flip the coin on them. There we go. And so that's what our exploit would look like. And so now, if we execute this function 9 more times, we should actually get the correct guess every time. And I'm not going to execute it 9 times because that will take a while. But let's do this. So we're going to have a look at our Ethernaut 3 exploit. And we need to actually deploy this to the chain first. To actually interact with this contract, we need to put it on the chain. And so this is all kind of set up. I don't think we need to mess with this. I don't even know. I probably should be changing that, but it doesn't really matter. And so let's deploy it. We get our usual MetaMask tab. I'm going to cost some gas. And let's wait for that to deploy. And then we can interact with it. Awesome. Extremely quick. And so now we have our exploit contract. Okay, and let's just put in true here. Guess that. Okay, and then we'll see how long this takes to execute. Hopefully not too long. How's everyone else been? Has anyone been doing out the challenges? There we go. That went well. Okay, and let's have a look if our guess was correct that time. We expect it to be because we've kind of rigged the system. We put our own contract and it's acting as a middleman and we're kind of getting in the middle of the RNG. So look. Okay, and look at that. We now have 2 correct guesses. Now I'm not going to execute this function 10 times because it will take a while. But let's try it once more again and see if we get lucky again. I'm going to try false this time. Maybe it's my psychic abilities. Let's try that. Okay. Here we go. Okay. And let's have a look. Here we go. And now we have 3 correct guesses. Okay, so to complete this challenge, all we need to do is execute that 7 more times. I did do that in my actual attempt at this challenge. It took a reasonable amount of time. If anyone actually knows any ways of executing those functions quicker, I'd be open to hearing it. But I think you do have to call them over and over again. Awesome. Any questions for that one? Cool. Okay, I guess not. Okay, we're going to have a look at another kind of interesting quirk of Ethereum's systems. Actually, I'll open up for some interactive stuff here if people want to have a look at number 2 just quickly. I'm not going to solve this, but if anyone can see fairly quickly or spot the issue with this, I will be moderately impressed. So I suppose the hint is you've got to claim ownership of this contract below to complete level. It says to use Solidity. You don't need to do that. I'm going to zoom out. If anyone can spot the issue with this contract, that's great. Because this has a very funny story behind it because it seems a bit stupid as a bug. Yeah, thank you, Garfin. Yeah. So the construction of this is just called something different, which sounds like haha, yeah, funny bug. Like that's not something legit would happen. And so yeah, here it's called fall 1 out, right? That's quite funny. But it actually, I suppose, there have been exploits like this before. And so what happened is, pull it up over here, so we have the story of Rubixi, right? And the company changed its name from Dynamic Pyramid to Rubixi with a contract. Right, and so this function here called Dynamic Pyramid And so the attacker just called the old constructor and claimed ownership of the contract and stole money. So it's not the cleverest exploit. It's not even the most technically intricate. It's similar programming bugs to other kind of more programming. It's a similar platform and there are similar issues. We're going to look at telephone, very short program, and then we might look at token or delegation if we have time. Delegation is quite. We want to take a look at this one if you know a little bit. If you don't, because reading about the delegate call method is actually really interesting, because what delegate call does is it will let you call another a function from another contract while maintaining the state of your calling context. And so in the Ethereum virtual machine, functions have, or contracts, sorry, they have certain slots of memory. So they're 32 bytes, I think, wide. And variables are kind of placed in slots in order of when they're declared or declared. And so what happens with delegate call is you actually kind of map your memory onto this, or you preserve that ordered memory and its state when you call the function that you're delegate calling. And so what that means is that this function here, variables in the slot 0 of this, when you're interacting with slot 0 of this function's any function's memory or this contract's memory. So here the first variable initialized would be onus, that would go in slot 0 of the delegate contract. I might draw a diagram actually. Here we go. So we have our delegate contract and we have our delegation contract. And so delegation has, I suppose, a little box of memory down here with some slots, and so does a delegate contract. So a little box of memory with some slots. And so we have in the first slot of memory, this is our let's write actually names up here. So there's a delegate, and this one's delegation. So our delegate contract has these slots of memory, and in these slots of memory, it places in the 0 slot, it places its owner variable, right? So, and so does, I don't know how to make this text more, but it places the owner variable there in this first slot. And over here in delegation, it does a similar thing, right? It declares a variable and it places it in this 0 slot. Okay. And so when delegation, you notice delegation also has this kind of delegate that it keeps track of. Okay. So that's, it might be in the same slot, it might be in the next slot down, I think. But anyway, we kind of get this delegate, we pass in a delegate address to the constructor. And so this delegation contract always is tied to this delegate contract to keep that as a delegate. And then the owner is the message sender, right? Typical behavior. Anyway, fallback function, like we've seen a few times before. And so we take the address of the delegate and we delegate call with whatever data is passed to the fallback function. Seems like a bad idea because we can kind of manipulate this data to get it to call whatever function we like. So we want to call this pwn function. And so it's, I suppose, slightly lower level because we're not necessarily, we're passing this data which gets passed directly to that function. And then we then message.sender, which is the result of message.sender for context, is the person who initializes this interaction. So we will assign the owner variable here to be sender of this message. So whoever calls this fallback function. But the issue with that is delegate call lets you, when you delegate this memory slot, this memory slot in delegation is made mutable, right, from the delegate contract, right? And so when we call delegate call, what we do is we take all of these, everything in here, and we just make delegates calling context that. And all the changes that are made to memory here get mapped back to memory here, right? And so what that means is that if we change the owner variable in our delegate or a delegate contract, even though the owner variable, you might say, okay, it's just this owner variable. This change gets mapped back to this owner variable. And so that's why the delegate call, it's I suppose it took me a while to get my head around to start off with. It's not the most effective, I don't think. It's useful, don't get me wrong, but it's easy to make errors with. And so it's an interesting challenge. And that's, I think, what a lot of these challenges are like, looking at intricacies of the Ethereum system, which are useful, but easy to get wrong. So I won't write the exploit for this challenge because I didn't prepare an exploit for this one, but we can look at 4 or 5. 5 is a fairly simple integer overflow. And so if people want to, I'll give this one away because I do like 4 because it shows an interesting feature of Ethereum. Anyway, token, if we have a look at this transfer function, oh look, we can pass in our address and we can pass in a value, right? And you notice we're working with UINs, unsigned ins, that's all right. And so we have this requirement here. So our sender of the message, their balance minus the value they transfer can't be greater than 0. Now, if you might, that might seem reasonable to you, it might not. But if I point out that we're working with unsigned ints, once again, then it will start to seem less and less reasonable because the way we're checking if our balance is fine, if we can make the change to our balance, is checking if it is greater than 0. And unsigned ints are always greater than or equal to 0, regardless of what changes you make to them. And so here, the value we pass in, say this is, so I think in this contract, we start with a balance of 21 or 20, sorry, and we need to get it above 20. So say if we pass in 21 as our value and our address is some random address, any account. So here we have the level was a contract that we could just send money to before. So we could pass it to level or person 2 or something. So if we go to level and then we pass in 21, so this requirement check, okay, so we'll do 20 minus 21, but as a uint. And so I think there's a uint 265s. So we'll just get some massive number here, and that's clearly greater than 0. And so then our balance will be subtracted from, we'll subtract 21 from our balance, we'll get a massive number, we'll add 21 to level's balance, which doesn't matter, and we'll return true. And so then we'll have a balance of something ridiculous, and we can then, just use that, win the challenge. Do we have time? Am I allowed to do one more, Leo, some committee member? I don't know.
I think the workshop's been going for a fair bit. Maybe if you quickly talked about, if you gave it a high level overview, maybe that could be good. Yeah,
awesome. Okay, I'll just quickly review it. So this is a fairly short one. I won't write the exploit. But the idea here is just a very, once again, same with a lot of these, is a very simple slip up. It's this here, right? So here we can change our owner, right? And so we have the owner declared as usual, fairly simple. And we have the change owner function, right, which is public. And so if tx.origin does not equal message.sender, owner equals underscore owner. Right? And this example here is a fairly kind of like sterile example, like you wouldn't see this exact thing in nature. But here, what the distinction is that transaction.origin, I might draw a diagram up. So here, transaction.origin in Ethereum refers to the person who initially kind of triggers the transaction, right? So if we have, say this is a person here, this blue box, and then we have a contract here that you're interacting with. So say this red contract. Now here, if we send a transaction to this red contract, we have our transaction, and let's call this person Bob. So here, in this first case, our tx.origin, so transaction origin equals Bob, and our message.sender also equals Bob. That's fairly simple. But here, say if we, in the second case, we put a contract in between. So we have a green contract that we're talking to. And so this red contract somewhere off in the world, we just want to talk to the green contract, or Bob wants to talk to the green contract. And now when Bob talks to the green contract, right? So he sends this transaction, right? And for this transaction, right, the tx.origin equals Bob, same thing. And the message sender equals Bob also. Awesome. And then for this second one, we have, say this green contract sends a message to the red contract on its own. So here we have our tx.origin equals green contract, right? Oh no, equals Bob. And our message.sender equals the green contract. So the transaction.origin is who initially triggered it, and the message sender is who actually sent this transaction. Now, the issue here is if we use tx.origin for authentication, that means that if or anything, right? All the transaction can have a transact with another contract if this is using tx.origin as its. You can make another contact in between, and you can change your tx.origin. So you can change your message.sender by doing that. Awesome. Thanks for your time. That's all I've got for today. These challenges are really fun. I'm not the biggest on Ethereum challenge, but they're very entertaining. So yeah, if you want to do something, please be my guest. Did anyone have any questions before we finish up?